there's been an exponential increase in our understanding of what causes Alzheimer's disease, how we can target it, and how we can treat it.
It really is miraculous that in a short period of time, which is really 25 years, and we know a lot about the disease.
We are at the brink of controlling one of the major diseases affecting world health.
We do have the research scientists, we do have the knowledge, and I think we can beat Alzheimer's disease.
The history of modern medicine is really tracked back to around 500 years ago when people decided that it might be a good idea to crack open the body and actually see where the disease is. If someone is bilious, is his liver really affected? If someone is demented, is his brain affected? And it's not that long ago, but that really gave rise to this idea that we actually have to see the disease to understand it. Alzheimer's was a German neuropathologist. His use of novel staining techniques in dead brain under the microscope allowed him for the first time to see this constellation of amyloid plaques, neurofibrillary tangles, and it ultimately justified calling this disease Alzheimer's disease. Now, it's interesting to point out that if you look at textbooks of neurology, psychiatry, medicine, for decades thereafter, into the 30s, 40s, 50s, there's nary a mention of Alzheimer's disease.
Serious and focused research on Alzheimer's disease really began when the National Institute of Aging and a variety of other researchers, brain researchers, realized that what we had been calling dementia or senile dementia or hardening of the arteries or arteriosclerosis in late life that everyone just called dementia, actually in the vast majority of cases was Alzheimer's disease, which before this we had thought had been this very uncommon disorder that occurred in your 40s or 50s in rare cases.
Once the field and the world recognized that this relatively common entity of senility, quote unquote, was a true disease, then it really justified a concerted research effort. In the 80s, we were able to isolate the main building block, the main peptide that makes up one of the core features that Alzheimer's himself saw, namely amyloid plaques. And with that information, we were able to identify the parent protein that produces amyloid, which is called amyloid precursor protein, or APP.
When we started, no one knew anything about what plaques or tangles, the things we see in the brain, were made of. We now know that exactly the proteins that they're made of. We understand the pathology and how the pathology developed at the microscopic level. We understand the processes that take us to amyloid plaques and how they damage nerve cells. And we also understand the very earliest aspects of what happens inside the cell that leads to neurofibrillary tangles in the brain in Alzheimer's.
In the 1980s, we made tremendous progress in first, understanding what the disease represents, second, how to diagnose it, and three, to understand something about how it begins in the brain, how it changes brain cells, damages brain cells, and results in its clinical phase, dementia, loss of memory and thinking ability. Tremendous number of tools have helped this remarkable advance. In 1991, the first gene mutation that causes Alzheimer's disease in an inherited fashion in a particular family was reported, and it happened to be in that amyloid beta gene. So within 10 years, the discovery of an abnormal protein, amyloid beta, in excess amount in Alzheimer's brain led to the discovery of the gene producing it, and then the gene, when mutated, causing the disease.
It's worth explaining why that's so important, even though early onset Alzheimer's disease is so rare. The reason is because until that point, there was really no idea, no clue as to whether amyloid plaques or neurofibrillary tangles, the hallmark features of Alzheimer's, were really causing Alzheimer's disease. And so once amyloid mutations were found, it argued very forcefully that, in fact, amyloid is really one of the main causes of Alzheimer's disease.
There are only 200 to 300 families in the world who have these kinds of mutations that lead to familial early onset disease. They are valuable far out of proportion to their numbers, because they're where all of the models, our mouse models that we can use to look to find drugs, all come from the genes in these families.
You can take that mutated gene and put it in a mouse. Take the gene that causes Alzheimer's disease, put it in the mouse develops a form of Alzheimer's. It's not classic Alzheimer's disease, but it certainly develops amyloid plaques. We began in the 1980s with trying to just understand what the disease represents. In the 1990s, we began to get some treatments that helped the symptoms of the disease, but now in this decade, we understand that the illness, in order to really be effectively treated, is going to require agents that get at the underlying mechanisms of the disease. Can we make antibodies that target amyloid in the brain? Lo and behold, in at least those transgenic mice, when a vaccination approach was employed targeting that amyloid by antibodies, it seemed to really have a remarkable effect. It removed those amyloid deposits. I never would have thought that. So then that led to a whole host of immune-based, antibody-based therapies. Not all vaccination, some infusing the antibodies. And there is great hope that they will be effective in clearing out the amyloid in the brains of people with Alzheimer's disease.
If you think about all the successes that we've made in medicine, they've really come on the heels of being able to visualize the problem, whether it's cancer, heart disease, various problems of the digestive tract, and in fact, brain disorders, stroke, MS, multiple sclerosis, tumors. One of the great challenges of Alzheimer's disease is the fact that until recently it's been relatively invisible to our technologies, and I think that's why it's been such a great challenge. But that, I think, is shifting now.
Pittsburgh Compound B, or PIB as it's known, is a radioactive tracer that you give in a vein that, when you do an image, shows you the amyloid plaques that are in the brain of people with Alzheimer's disease. It will absolutely show you plaques in a living human.
I think it's going to revolutionize both how we do research, as well, if we continue to validate this technology of imaging brain lesions, it will eventually be very helpful for general practice in diagnosing the disease.
Okay, you're good to go.
We now have optimized a MRI-based technology that allows us to really capture the earliest stages of the disease. We now know very clearly that there's an earlier stage of Alzheimer's that can be called the cell sickness stage, where the cells are there, but they're just malfunctioning. The good news, though, is that if we could capture that stage of the disease, it really, I think, offers a lot of hope for better treatment. I think it's obvious to say that it's easier to treat a sick cell than a dead cell. And in fact, now as we've finally entered in an era of drug trials for Alzheimer's disease, I think what the future is going to bode is an attempt to really try to capture people who have this cell sickness stage, as difficult as it is to detect, because it's going to be that stage of the disease that's going to potentially benefit most from treatment.
We've made a paradigm shift. At least our research is dedicated to the proposition that we don't just want to wait till the disease is fully manifested in the dementia stage, but we want to make a commitment to seeing if we can't prevent the illness.
We will find a drug that slows things significantly, and then we'll figure out what it does and what it doesn't do and make a better drug. And then we'll add two drugs together, because many of these drugs that attack different aspects of the disease could be used together. And we'll do the same thing that the oncologists, the cancer docs, did with lymphoma and leukemia. Will slow down this disease process, an inch at a time, with luck, with a good drug, a foot at a time. But we'll get there. And I can say that in the 80s, a lot of the people who were senior people in the field thought, there's no way you can ever help this disorder. There's no way you can find a way to attack these things. We don't know what they are. So in 20 years, we've come to the point where our expectation is that we will find things that will slow things down. Our only sorrow about this is we can't do it instantly. The nature of the disease is such that it takes time to prove that the medications work.